Good afternoon, everybody, to this pre-lunch session. Okay, it is a pleasure for me to be present here and to give this seminar in this conference in honor of Professor Sinha. So I know Professor Sinha since the later part of 1980s, actually, when I used to go to BCC to do my computational work as a PhD researcher. And this interaction grew stronger and stronger over the years. And he encouraged, supported, and inspired me a lot. So in the next 30 minutes, I will take you through the journey of a low-energy nuclear physicist to the domain of astrophysics with the new generation of radio telescope. So this is one of the many brainstorming sessions with Professor Sinha. This is particularly with our Shah Institute colleague. We are discussing education and research in this. Okay, let me start with this. A bit of history of science. In 1931, Subramanian Chandrasekhar actually demonstrated that it is the relativistic degenerate electrons that gives stability to the white dwarfs. And he also predicted the mass limit for white dwarfs. So this was the end of the story for white dwarfs. But others, actually, visionaries were thinking in other directions. For example, what happens to stars more massive than those actually evolving to these white dwarfs? Now we know this actually definite limit or the masses of progenitor star which could evolve to a white dwarf or otherwise to a neutron star or black hole. So this distinction is made at the 8 times the solar mass. So one such visionary is Lev Landau. He was thinking about what will happen to the more massive progenitor stars. Okay, and the other two, those are observers. I will tell what they did actually. Okay, this was a paper written by Lev Landau in 1931. And he was dealing with this more massive progenitor star and their fate. And he made actually one very important statement in this paper. I read for you. The density of matter becomes so great that atomic nuclei, they come in close contact, forming one gigantic nucleus. This is perfectly a true statement. We will see that. Okay, this paper was written in 1931, but it was published on 29 February 1932. So you got it right that 1932 was a leap year. And the discovery of James Chadwick's neutron was published in Nature 2 days earlier, that is 27 February 1932. So Landau had no idea of neutrons. So he did not talk about neutron star or compact objects like that. But these two people, on the left, Walter Baade and Fritz Zwicky, they made actually profound statement after the discovery of the neutron. What is their statement? It is at the bottom. So I read it. Supernovae represent the transition from ordinary star into neutron star, which in their final stages consist of extremely closely packed neutrons. And just 2 sentences above, they also predicted that cosmic rays are produced in supernovae. So you can see 3 things: cosmic rays, the connections between supernovae and neutron star, and a new, actually, compact object called neutron star. 3 predictions in this half-a-page actually report. This was actually, they made this statement in the Stanford meeting of APS in 1933, and this half-a-page write-up was appeared in 1934. So I do not know whether this kind of prediction was done by any other physicist, where 3 predictions came out to be true later. So you can call them visionaries. Okay, so there was a wait between 1933 to 1967. This was the discovery of first pulsars by Jocelyn Bell and Anthony Hughes. So you can see this regular encircled fix actually in this graph paper, and this date is written here, 28 November 1967. Okay, recently, I think just before the lockdown, we tried to actually get Jocelyn Bell here in this auditorium to give Saha Memorial lecture actually, with the help of Professor Subi Shankar actually. But it did not materialize because she was traveling a lot. She could not submit her passport for the visa. But anyway, his mentor or supervisor, PhD supervisor, Anthony Hughes, delivered the Saha Memorial lecture in Saha Institute in 1993, if I correctly remember that. And recently, Professor Vikas Sinha wrote a very nice obituary on Professor Anthony Hughes in Telegram. Okay, so what you see here is a neutron star, rotating neutron star with a very high surface magnetic field. What does it mean? Take us a simple picture of this magnetic field. This has a dipolar configuration. So a dipole is rotating and it will emit electromagnetic radiations. Those are the pulses. This is very similar to the accelerated charges radiating electromagnetic radiation. Okay. So next big discovery with this neutron star is the Accelerator pulsar. So this is a binary neutron star system. One of them is a pulsar, other one is a neutron star. So just we have seen that these pulsars are emitting pulses, and these pulses are being observed from the Earth at regular intervals. But they also emit gravitation onwards. So what does that mean for this system? Immediately, it is David Schramm and his collaborator. Immediately they calculated that these 2 neutron stars will collide in 300 million years. Very good. And these pulsars were discovered by Russell Halse and Joe Geller in 1974. And the discovery of the first pulsar was awarded Nobel Prize in this year, that is 1974. Okay. So here you have seen that 2 pulsars are going around each other, and as they are emitting gravitational waves, their orbit is coming closer to each other. And so this decay of the orbit actually was calculated and plotted in terms of time, or here it is in the x-axis years. What you see here, all these dots actually are the observational points of these pulsars in this Accelerator binary system. And the solid line is the prediction of the Einstein general theory of relativity. And this was the first indirect actually detection of gravitational waves. And Russell Halsen and Joe Taylor were awarded Nobel Prize in 1993 for this discovery. Okay, another beautiful neutron star system where both neutron stars are pulsars. This is a called double pulsar system, and this is, I think, only observed so far double pulsar system. And these two pulsars are actually are called pulsar A, which has a mass 1.337 solar mass, and the other one, this is lighter one, has a mass 1.25 solar mass. But why this system is so important? Because you can test the various gravity theories here. But so far, this general relativity is coming out in flying colors in all these states actually. So such a profound theory is general relativity. Okay, and for this system, one can calculate various actually post-Taylorian parameters actually. So this is a binary system. One can calculate masses of this system, binary system, using Kepler's third law. But you need still some more observational things like orbital precession. This is gravitational redshift and time dilation. Decay of the pulsar orbital period actually, and Sapiro delay, two parameters, R and S. All these things are actually functions of masses of masses of this double pulsar system, and other things like eccentricity and some other constants. So I showed here 5 actually Keplerian post-Keplerian parameters, but this system actually measured 2 more actually, 7 such post-Keplerian parameters. Okay. Okay. These things gone out of the detail. Okay, this is about I will discuss here in the next slide section. So far, there are roughly around 3,000 neutron stars for which we know their masses very well, particularly in the binary systems. This is a compilation of that, and you can see here, this is the most accurately measured actually a neutron star with a mass of 2.01 solar mass plus minus 0.04 solar mass. Here. Okay. So the radius measurement of a neutron star is much more a difficult job. Traditional way to measure this one is just first connect the fluxes from the neutron star surface, then feed it with a black body, and from there one can estimate this radius of a neutron star. But there are lots of uncertainties, like what is the atmosphere around a neutron star, and then the distance between the observer and the neutron star. Because of that, this measurement is not very accurate. Now, there is one experiment actually. is attached to the space station. This experiment called NISTAR, that is Neutron Star Interior Composition Explorer. What is that? Or what they are doing? You can see that two rotating neutron stars, and you can see some white spot on them. On the left, there are two such spots, and on the right, there are three such spots. These are hot spots actually, because very similar to the sun's hot spot. These are because neutron stars have very high surface magnetic field, that is on the order of 10 to the power 12 gauss. Now, these hot spots are emitting actually X-ray photons, and this space station experiment is actually collecting those detector collecting those photons, and those photons actually they are under the influence of this strong gravitational field of the neutron star. So what they do actually here, they make a pulse profile model for this, and they fitted the data with them, and from there they came to know about the ratio. This is compactness, we call it mass of the neutron star divided by radius of the neutron star. And this actually, so for two such systems actually, neutron stars actually, this has been radius were measured, and in both cases actually, masses were accurately known from radio observations. Now, we know the masses accurately, we know from pulse profile modeling the compactness m by r. So we know the radius of this neutron stars. And this radius actually coming out to be from 11 kilometer to 14 kilometer. Okay, come back to this another measurement actually using this double pulsar system. Now we can measure the radius of the both pulsar systems are using this actually spin orbit coupling. What is this spin orbit coupling? This picture is all black actually, not very well seen from the back diagram. But okay, this is the equatorial plane, and the other plane, which is the orbital plane of the pulsar. So this orbital plane is precessing around the total angular momentum. Fine. So as a result, the pulsar's actually angular momentum, orbital angular momentum is changing, and this is compensated by the spin precession actually, both the pulsars. So they change to keep the total angular momentum constant, and this is called the spin orbit coupling. Okay, the spin orbit coupling is has a totally different meaning in quantum mechanics, atomic physics, and nuclear physics from this one. But what is the point here? So this orbital plane is shaking. That means the pulsars actually, pulses are direction is changing. So its time arrival from the pulsar to the observer will change. So what is this change actually in the time? Is delta T0 is given in terms of the, for example, for this pulsar A actually, this is moment of inertia, and all other quantities like mass, then pulsar period, orbital period, and two angles. One is the angle between this spin of the pulsar A with respect to the orbital plane or orbital angular momentum, and the other angle I is the inclination angle. So inclination angle is very accurately known as 90 degree, but so far there is no actually misalignment between this spin of pulsar A with respect to the angular momentum, orbital angular momentum axis. So as a result, this theta A is 0. So there is no noticeable change in this timing, arrival timing of the pulsar. But there is another way actually to measure this spin orbit coupling, that is the Alfvé's radius term. So this has delta V. This is actually the expansion in velocity of the pulsar divided by speed of light of the pulsar in given powers. So this is beta 0 actually. Beta 0 square means V by C whole square, first term. Second term, 2Pn term is V by C to the power 4 contributions. And then this coming is P orbit coupling for the pulsar A and pulsar B. For pulsar, so you see that this is a very tiny effect actually. And it is competing with this 2Pn term. So when this actually exceeds this 2Pn term, only there will be an appreciable measurement. And this term beta S actually, which is appearing here actually in pulsar A. For pulsar B, this term is negligible. The speed is so small that one can neglect it. But this term beta S actually contains the moment of inertia of the pulsar A. So dimensionally we know that moment of inertia is mass times area square. And for this double pulsar system, both the pulsar, mass of the pulsar A is very accurately known. So we can measure this radius of this pulsar very accurately without much actually trouble like this. What we can do. These are, I would say, free of contaminations of errors coming out of the atmosphere of the neutron star or the distance between the observer and the pulsars. So what all this actually imply? So they imply constants of the equation of state of matter inside the neutron star. Okay, so this is a nice picture of this neutron star structure. And neutron star actually is a very good system to test all kinds of physics here. Condensed matter, particle physics, nuclear physics, electromagnetism. So such high rich physics actually are involved in this neutron stars. And